So good morning, everybody. Welcome to the final class. Of course, be aware, the final test coming up, which is open Monday, this upcoming Monday between 7 and just before midnight, same format as previous two tests, only it's a little bit longer and thus worth a little bit more than the previous ones, so study for that. And obviously the material is just from the time of the second test. So, I'm going to continue with the science lecture. Been a little under the weather, so we'll see how well this goes. But we'll continue with the material here. It might not be a full-length class, but just depends on how long it takes to get through the rest of the material today. So, last place we left off, we're just talking about the possibilities of life on other planets. And I was saying that it seems highly probable that there is life on other planets, but we're also discussing the issue of imaging exoplanets, meaning planets outside of the solar system, and some of the problems of that. This gives you a comparison to give you an idea of just how different planets potentially could be. If you took North America and dropped it onto the surface of Jupiter, that's how small it would be. So it gives you an idea of how much larger Jupiter is than the planet Earth. And scientists have had some success with detecting the presence of Jupiter-sized planets in other star systems, especially when they're close to their stars. Again, they haven't seen them, but they can detect the presence of them. By the way, it seems evident that you could not have a rocky terrestrial planet the size of Jupiter. They say that any planet that's large is necessarily a giant ball of gas. So you wouldn't actually have a kind of Earth-like planet that size, but nonetheless a kind of interesting point of comparison. Now, the question of is there life on other planets leads, I think, inevitably to the question of is there life like us on other planets? If we go on the basis of that, yes, there are living organisms scattered on other planets throughout the universe, well, what about the possibility of life like us? Now, I would say that that's a little bit of a trickier question to answer, because I think our immediate inclination would be to say, yes, why not? Because what has happened once can happen again, and if a species like humanity can develop here on Earth, well, why would we say that it's impossible for an analogous species to develop on another planet? But I think before we get excited about the prospect of ET existing out there, we should probably throw in a couple of qualifications here. First of all, we should probably specify what exactly we mean when we say life like us. And I think there are a lot of different ways we can think about that, but probably the obvious way is to say a species that has undergone the cognitive revolution. So a species that has developed the ability to process and transmit and understand information at a phenomenal level of complexity and detail. And that leads into the idea of a species that we can maybe communicate with in an in-depth way by learning each other's language or learning each other's vocalization. So maybe that's what we mean when we say life like us, just another species that has undergone something like the cognitive revolution. Well, I would say as soon as we frame it in that way, there are some kind of impediments that maybe come immediately to mind, because we only have one case study to work with, which is the planet Earth. And what our case study tells us is that a species like humanity is exceptionally rare, is not a common occurrence. Because you think about all the species and organisms that have lived in the history of the Earth. Earth has been habitable for 1 billion years or more. And there have been how many different species during that time? Millions and millions of species and subspecies all across the history of our planet. And as far as we understand it, as far as we know, humanity is the only one of those species that has ever experienced anything like this, anything like the cognitive revolution. Neanderthals, as I mentioned before, that might be potential exception if we consider them a different type of species, but that's not even really clear. And not only that, but the planet has hosted life for a very long time, and humanity only emerged quite recently in its history. So think about the dinosaurs that were here for millions and millions of years, and again, as far as we know, none of them ever experienced anything like the cognitive revolution. So if we take the Earth as a case study, maybe it's a type of atypical occurrence for this kind of species to emerge from nature. Not only that, but I would say the further along we go, the more we begin to grasp why humanity might be a rare type of species. There are considerations we should take into effect. Here are two ones. I'm sure there are more than two, but just two that we can pause over for a moment. First, the impact humanity has on its surroundings. Now, we should probably understand immediately why a species like humanity is not particularly a good thing for an ecosystem, because the problem with a species like us is it just takes everything over. It just dominates the ecosystem to such an extent that a wide range of animals become subordinate or dependent on humanity's presence. And indeed, the species itself has the potential to narrow the biodiversity and to even perhaps trigger an extinction event. So if you just frame it in those terms, from an ecological evolutionary perspective, the existence of a species like humanity is not necessarily a positive thing for nature as a whole. That's one consideration. And the other consideration is the complexity of the species as a whole. I don't know if nature necessarily favors complexity. In fact, if you look at the history of the Earth, what you see is the thriving of simplicity. And I mentioned insects previously. Insects is the kind of original inhabitants of the Earth. They've been here before we got here. They're still going to be here after we're gone. And there are some insects that have been here for millions upon millions of years, including one I'm going to mention shortly, without even undergoing much in the way of biological evolution. What is the key to the success of insects? Well, they're simple beings. They don't really require a lot to feel at home in their environment. The lack of complexity is something that allows them to be very adaptable and flexible to changing situations and circumstances. We have the sense, I would say, that humans are not simple beings, that we're complex organisms, and thus we have the impression that we require a lot to be comfortable in our environments. Indeed, it's one of the effects of the cognitive revolution that it's created this distinction between us and the natural world. I don't know if this is entirely true or not, but we, I think, have the impression of, particularly in certain societies and cultures, that we don't really fit into nature very well, that we're not kind of comfortable with the natural environment just at face value. No, we have to remake everything. We have to kind of redistribute and restructure the entire apparatus framework of the natural world. Look at all the stuff that we build. All these kind of massive buildings, skyscrapers, cities, highways, all these things constructed out of the natural world for the sake of our own expediency and convenience, to make us more comfortable in our surroundings, more comfortable in our environment. I mentioned something specific there, resource and energy usage. You have to say that humans, on the whole, from an evolutionary standpoint, are not necessarily energy or resource efficient beings. That's part of the reason why we have the impact on our environment that we do. Think of this as a point of comparison, contrast to, say, dinosaurs, for instance. How did dinosaurs survive for so very long? Well, in part because they were energy and resource efficient creatures. There you see a comparison between a brachiosaurus, massive creature, compared to an elephant, a giraffe. We're used to thinking of elephants and giraffes as being very large animals, but not compared to a brachiosaurus. And yet, here's a surprising piece of information that has come to light recently. It's possible that a brachiosaurus ate as much as an elephant in terms of its actual food intake. And you'd say, well, wait a minute, how is that even possible? The animal is so much larger. Yes, but a much more resource and energy efficient animal when you get down to it, making the most of what it has. And part of the thing with the dinosaurs, too, is their general lack of investment in their offspring or raising their young. They say the thing with dinosaurs is they would often just lay eggs and then leave them there, not even expend any energy and resources on nurturing or tending their offspring. In fact, a lot of dinosaurs, when they would hatch, they're already self-sufficient. When they come out of the egg, they're already able to fend for themselves. Think about that as a contrast to humans. How much energy and resources do we expend on raising our young, raising our offspring. I mean, if you think about us in those kind of animal terms, right, creating our nests, our layers, like these houses or these apartment blocks, and buying cars so we can drive our children around, and working and buying food and all of that stuff. It's an enormous drain on energy and resources just for the purposes of raising our young, just for the purposes, in biological terms, of procreation. And we maintain lifelong relationships with our offspring. I think that's unique among all animals. Animals do form attachments at different stages, but ours is lifelong parent-child interactions. There's a point that I mentioned previously about insects. Estimates indicate that varieties of mosquitoes have been around for close to 100 million years. That's how long those flying bloodsuckers have been around. Back to the age of the dinosaurs, in fact. They were biting dinosaurs back in the day. And remember the Jurassic Park story? That was supposed to be one of the ideas as to how they could actually clone dinosaurs, because they were being gorged with the blood of dinosaurs, and you could recreate the DNA of the dinosaurs. Not so, as it turns out, but it was actually good science at the time in the 90s. The problem is DNA erodes very quickly. It doesn't keep the course over millions upon millions of years, but it was actually something that was relevant in the 90s. Mosquitoes have probably undergone very little in the way of evolutionary development over 100 million years. From their perspective, they don't need to change much, right? They're doing just fine as they are. I mentioned this as a thought experiment previously. If you had to guess, would you say that humanity is somewhere near the beginning, middle, or end of its life cycle, if we go on the idea that we're 50,000 years in right now? And as I said, that is one of those unanswerable questions. But if I had to guess, if I had to give you some kind of answer to that, I would say that we're probably somewhere near the middle of our life cycle right now. And why would I say that? Well, because it's near the middle when you would expect to find the most people. That's where you would have the biggest glut of humans, and that's what the estimates tend to indicate, that the population numbers are reaching their peak level, topping out at 10 billion or something like that, after which the expectation is they would go into a gradual process of decline, and to an extent they have to go into decline in the future. It's not sustainable for a human population to continue to grow over time. And that's a purely kind of quantitative estimate. You say, okay, when the numbers go into decline, that means that we are towards the back end of our life cycle. So that would mean we would last for another 50,000 years. Now, you might say that actually sounds a little bit generous. What about climate change and deforestation and the impact we're having on the environment and all those things? What about nuclear warfare, all of that stuff? The possibility to wipe us out much sooner than that. Well, that stuff could actually end human civilization. But the destruction of our civilization, the destruction of all the stuff we build, all the cities, would not necessarily mean the end of humanity itself. Species could continue to survive without civilization, proof of which is that our ancestors did for a very long time. What about things just like fossil fuels? What if it's the case that we exhaust the fossil fuel resources and actually don't find the viable alternative to replace them? Well, industry would regress. It would shut down. We wouldn't have the energy that we have today, but there would be a movement towards what we might describe as a more primitive state in the future. And we're used to attaching a kind of value judgment to this idea of primitive as though it's negative, but not necessarily. It just means less technology, less apparatuses, less infrastructure. We're used to thinking of this kind of linear forward development, always better, always more advanced. But that might not be the future of the species. There might be this kind of movement backwards at some point in the future, and that would take us into the end of our lifespan. Of course, the key point there, another 50,000 years, it's hardly 100 million years, right? It's a big difference in terms of the life cycle of a species. Let me talk about these things, and it kind of leads us into the question of exploring beyond our planet, because when we're aware of our basic finitude, the kind of limitations of ourselves as a species, we become more curious about the possibilities of branching out or reaching out across the cosmos, especially this idea of seeing, well, what exactly would organic life look like on other planets or on Europa, for instance. And so this takes us into the question of what exactly can we do in the way of communicating with potentially other intelligent species or traveling. Well, how far can we really travel across the cosmos? Well, nowhere, probably, is the answer. We have been to the moon, right, and potentially Mars. I mean, that's something that they're certainly working on right now. Only unmanned spacecraft have been to Mars up to this point. We're certainly interested in going there. But in terms of making face-to-face contact outside of the solar system, not a likely scenario, just for simple practical reasons. Now, yeah, Proxima Centauri, which is the closest star to Earth beyond the sun, which is located about 4.2 light years away, which actually doesn't sound too bad. I mean, that literally means that's how long it takes light to reach us from that star, so it's traveling for 4 years. But make no mistake, 4.2 light years is a phenomenal distance. It's nowhere close to us. It is so much further than any of the planets, and here's the kind of evidence to show us that. The famous Voyager 1 spacecraft was launched in 1977. And it is famous for making a kind of circuit, a tour of the solar system. And it's given us some fairly spectacular images of different planets, like Jupiter. And Voyager 1 was in the news recently because there is talk about it now leaving the solar system. Although that's a little bit ambiguous in terms of where the solar system actually ends. But we'd say, well, there are no major planets class Neptune, for instance, so we can kind of go on that. And Voyager 1 is still transmitting a signal as of now, although it will probably die within the next couple of years, even though it has late 70s computer technology aboard it, because obviously once you launch it, you can't update the computer technology, so it's totally primitive by our modern standards, but still transmitting a signal right now. It will soon fade out. So, Voyager 1 has completed a kind of tour, a circuit of the solar system in over 40 years. Well, traveling at its current speed, it would take it 73,000 years to reach the next star. So that's how far away Proxima Centauri actually is from us. So I don't see us necessarily sending out people on these kinds of expeditions. I mean, there are just intrinsic barriers. In fact, there are intrinsic barriers within the laws of physics itself. 4.2 light years. Now, as far as science understands it, the speed of light is the absolute top end speed for anything in the universe. Nothing can travel faster than the speed of light, and nothing that has any mass or material can travel at the speed of light. That includes us. We have mass as well as the spacecraft that we develop. So in other words, 4.2 years is the absolute fastest that anything whatsoever could reach this star, regardless of what technology we develop in the future. Well, we don't keep people in space for 4.2 years, even at this point. So this gives you a sense of the distances involved. So, direct face-to-face contact, probably not. I mean, you like to be optimistic about these things, but it's not a likely scenario at all. Having said that, however, we do send things at the speed of light. We certainly transmit signals at the speed of light. We have made incredible use of the different wavelengths of electromagnetism. That's what it means to send things at the speed of light. For instance, your Wi-Fi signals are moving at the speed of light, hence the reason we get our internet connection so quickly. And this is something where we're interested in perhaps sending out signals at the speed of light to see if we get any messages in return. There you see a kind of a simple message that was sent from the Arecibo Observatory back in 1974. It was beamed at a dense star cluster located about 25,000 light years away. So that is how long it would take for the message to actually arrive through space. This wasn't really a serious thing. It was more of a kind of publicity stunt, but it gives you kind of a sense of the idea of sending out simple signals, beaming them at other star systems, or sending them out at dense clusters, and seeing if we get a message in return. Obviously, there's a lag or a delay, but if there are other creatures watching the skies, are curious, then perhaps they could intercept the signal and respond to us. Thus, we could have that kind of long-range communication. Well, we're certainly paying attention to these things. We're scanning the skies ourselves, looking for any kind of signs of life, any signals, deliberate or otherwise. And so far, nothing. Just a dead air. There's been no signs whatsoever, no noises coming from above to give any indication of intelligent life attempting to communicate with us. unless there's some big government conspiracy cover-up or something like that, but probably not, right? And so as it stands right now, we feel as though we're kind of alone, at least from our perspective. That's actually a paradox. There's a term for it. It's called the Fermi paradox. Fermi paradox refers to the lack of any kind of signification of intelligent life out there. And here's the reason that it's a paradox. The Earth is 4.6 billion years old. The universe is 13.8 billion years old. Therefore, the Earth is relatively young compared to the universe. So you take that into account, it stands to reason that there have been planets before us that have existed, there have been species before us that have existed, and perhaps species that have undergone the cognitive revolution in the past. So they preceded us. So we're used to thinking about kind of alien encounters or sci-fi encounters as a futuristic thing, but it is certainly reasonable to say that there have been very advanced civilizations and alien inhabitants that have been here in the past. And I think that's a kind of relevant idea to take into account. So the paradox would say, well, if these species did exist, why don't we see any signs of them today? Why didn't they work to create some kind of lasting impression that would transcend their own particular finite existence and give us some sort of indication that they're out there? We have two potential reasons. Again, I would say more than two potential reasons, but here are, like, say, the two biggest explanations for the Fermi paradox, one of which is pessimistic and one which is more optimistic. The pessimistic explanation would say that species go extinct, and that's basically what happened, and they might go extinct over relatively short periods of time. So yes, certainly possible that some species underwent the cognitive revolution in the past, built advanced technology, sent out long-range radio transmissions, sent space probes out. Who knows what they were trying to do? But the species just died out a long time ago. Their technology fell into disuse and decay, and we just missed each other. It's just too much space and too much time for us to cover in order to kind of sync up in that way. And that makes, to me, a certain amount of sense. You have an image of the Andromeda Galaxy, which is the closest galaxy to the Milky Way. You have a sense of a galaxy with its billions of stars, all its many planets, again, living organisms probably on some of those planets, other alien species, advanced civilizations, etc. Yes, they certainly exist there. They might try to communicate over long distances. Well, it is a very long distance to cover, but also time is an impediment as well. We stop and think about it for a moment. How long have we been capable of detecting long-range transmissions over space? How long have we really been interested in this idea of scanning the heavens, looking for the signs of intelligent life? It is not a long time relative to our lifespan of a species. What, 100 years or maybe a little bit more than that? Think about that relative to the lifespan of humanity as a whole. And then expand that to the ecological history of the Earth. When we talk about evolutionary history, cosmic history, we're talking in terms of hundreds of thousands of millions and billions of years. So if we're really only capable of doing these things for a narrow window, then it's impossibly small. It's too much like trying to drop a marble from outer space and hoping that it lands in a plastic cup floating in the ocean. Just too much of a kind of narrow space for us actually to hit that sweet spot of communication. Certainly a possible explanation as to why we're not actually detecting anything as of now. Yeah, question?
What's the difference between that galaxy and the Milky Way?
The difference between that galaxy and the Milky Way, well, Andromeda, I believe, is a little bit larger than the Milky Way galaxy. But, of course, when you look at a galaxy from a distance, it kind of all looks the same, right? Big spiral structure. And this is just a product of us not seeing things up close. And I'll talk a little bit further about this. The kind of uniformity of things is kind of like looking at stars in the sky, where you just see these points of light, and that's because we're so far away, thus you see uniformity. But if we could zoom in, then what a fascinating sight to see the planets up close and to see the diversity. So the other reason, which I would say is a more optimistic reason, would say we're just not looking in the right way. We're just not kind of examining the situation properly. That, too, I would say, is a perfectly valid explanation because that has been part of our history as well. You think about the history of geology, paleontology. Well, we had all these rocks and fossils in front of us for many years, and we weren't necessarily examining them in the proper way. It's only in the 19th century, for instance, the study of rocks starts to tell us how old the Earth actually is, completely reorients our understanding of the planet. Think about the fossils, the bones of the dinosaurs. They're there in front of us. They're there to be discovered. Evidence shouting out at us, look, there were these creatures here millions and millions of years ago, but only really in the 1900s that we start to actually see that and notice that. So maybe so too with the cosmos. Something there that's just shouting out at us, look here, and we're just not detecting it properly yet. As I say, perfectly valid explanation. Now we move into the final topic in the class, which I would say would be the broadest topic in a class that already has a lot of broad topics in it. And here is another one of these topics which takes us into, as I say, cosmic history in the most expansive sense. This is about the origins and future of the universe as a whole. And the Big Bang. The Big Bang theory, which we'll talk about, is the consensus view for the origins of this universe. Things we don't know, and make no mistake, when we start talking about the universe and the history of the cosmos as a whole, the things that we do not know are always going to outweigh the things that we do know. In fact, I would say that's probably true in just all fields that you care to name. There's no kind of comprehensive knowledge. There's just these little snapshots that we can sort of discern over time. Beyond us, galaxies, black holes, and quasars searching for light, and the multiverse and the infinite. So the Big Bang theory, which I'm sure you've heard about, even named a TV show after it at one point. Here is a theory that has obtained near consensus support among cosmologists, despite being very bizarre for two major reasons. And something that I should point out right from the start is this consensus support for the Big Bang theory is quite a recent phenomenon. Up until, I would say, the 1960s, there were different competing theories, including one called the steady state model. But it was only in the 60s that people started to accept the Big Bang model as basically describing the origins and basic structure of the universe, and it was nothing more than the accretion of evidence over time that supported the Big Bang theory. So empirical evidence, indicators that the theory is correct, that is what has led to a near consensus view, not universal consensus, but is very widely accepted in the scientific community, which itself is unusual because especially when you get into a subject like cosmology, often you have a lot of competing theories, especially when you start talking about things like the basic structure of the universe. But the Big Bang theory is very well entrenched right now. It's, as I say, very bizarre for two reasons. The first reason is that it clearly dates our universe. It says that our universe had a specific starting point 13.8 billion years ago. Now, we might be accustomed to thinking of something as being infinite. I mean, we know we're not infinite beings. We know the Earth and the solar system is not infinite. But surely space or existence or time or whatever, surely something out there is infinite. Well, the universe that we're standing in right now is apparently not infinite, but is finite, at a particular moment of birth, a moment of inception. Maybe it also won't last forever. So count the universe among the things that are finite or mortal, so to speak. Really incredible kind of implication of the Big Bang theory. And it's also bizarre just for what it basically proposes, the kind of idea of a point of origin for the universe, saying that this universe that we're in right now with its incredible vastness in space emerged from out of a vanishingly small point. So expanded outward from this kind of starting point. And here is the kind of a theoretical model, the kind of mathematical model. It's difficult for us to even kind of picture this in any concrete sense, but as far as they say, as far as they can tell, at its moment of appearance, the universe was squashed into a Planck length and was heated to 10 to the 32 degrees Kelvin. Kelvin is just a universal system for measuring temperature. That's obviously extremely very hot. I mean, at that level, it barely even matters whether you're talking about Fahrenheit or Celsius. It means unbelievably apocalyptically hot. So basically what the model says is that its moment of origin in the universe was this tiny infinitesimal little nugget of energy, extraordinarily dense, extraordinarily hot. A Planck length. What's a Planck length? How small is that? It is said to be 1.6 times 10 to the minus 35 meters, 0.000 on 1/6 meters, so ridiculously tiny, smaller than an atom, an electron, or anything else. This is theoretically the smallest possible space that anything can occupy in the universe. How small is that? Well, consider if you took one walnut and magnified it to the size of the entire universe, not the size of the Earth or the solar system, but the entire universe, and you were looking at it, you still would not be able to see a Planck length inside of it. Presumably, you'd be able to see elementary particles zipping about because it'd be so magnified, but you still wouldn't see this smallest possible length. So, as I say, it's a very kind of a strange, preposterous theory which proposes that all of space, energy, and matter expanded outward from this tiny point. This is something I've been working on recently during the course of the first second of existence, immediately after the Big Bang. You don't really need to know these, but I just thought I'd put them up there to give you a sense of the immediate time frame. There were 6 initial epochs that the universe is said to have passed through, all in the space of its very first second of existence. Planck epoch, grand unification epoch, inflationary epoch, electroweak epoch, quark epoch, hadron epoch, all hyper-accelerating through in the space of a single second. And there you see a kind of rough chronology of the universe. As I say, 13.8 billion years old, or 13.77 billion years old. You have this moment of origin attributed to quantum fluctuations. Period of inflation, this kind of expansion outwards from this tiny point. The dark ages, where nothing much happens. First stars form about 400 million years ago, and then you have this kind of long period of time where you have the development of galaxies and planets and all these things happening. Dark energy, I'll explain what that actually refers to in a moment. Basically, it means the universe is still expanding. And the question is, the burning question is, what came before the Big Bang? Because we have to think for a moment, 13.8 billion years is not forever. That is not the longest stretch of time that we can imagine. In fact, we throw around numbers that are much larger than that. So if this universe had a particular moment of inception, what preceded it? I mean, was it just pure nothingness? Or was there some kind of state of existence that came before the Big Bang? No answer. Science has no answer to that question. It does not know what came before the Big Bang. Theologists speak about the idea that the Big Bang was actually divinely ordained, or this was something that was instigated by God. I mean, that's as good an explanation as any, because we're working with an incomplete text. All we can see is this universe, and it is a barrier to anything else. We're incapable of seeing beyond our immediate framework of space and time. So we're not going to answer that question of what actually caused the Big Bang to happen, what came beforehand. This is as good a place as any to kind of get into this idea of the various things that we don't know. And I mean, of course, science can explain a lot about where we've come from and the development, the evolutionary growth of humanity as a species. Also, where we're going in the future. As I said before, the idea that the Earth itself is not an eternally habitable place, should not be capable of sustaining life forever. But make no mistake, there are plenty of things that science does not know, is not actually providing us any concrete answers. For instance, here you have a standard model of elementary particles. That basically refers to the kind of smallest, tiniest component parts of all the structures and things that exist today. So you take anything, a person, a planet, a rock, a plant, a giant cloud of gas, a star, anything whatsoever. Break it down steadily into its smallest parts. You get smaller and smaller down to the level of molecules or atoms, and finally down into the smallest constituent parts you can imagine, the elementary particles. And every single thing is made up of this stuff. You have your quarks up there with their very interesting names like strange quarks and charmed quarks. You have these particles too. Electrons are the most important ones. You also have the so-called bosons as well, which are force carriers. And these are all linked to the four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Those are the four irreducible forces in the universe. Gravity you know about. Thanks to gravity, we're standing on this planet right now. Electromagnetism, very instrumental in things like visible light. It's thanks to electromagnetism that we can see anything right now. And the strong and weak nuclear forces, a bit more obscure, but no less important. These things, these particles and these forces are the building blocks of existence. But why are they the building blocks? Science doesn't know. It doesn't have an answer to that question. It knows how gravity works, but it doesn't understand why gravity exists in the first place. Why should it exist in the first place? We could say, well, on the one hand, it's kind of convenient that it does, right? Gravity causes stuff to clump together, forms planets, forms stars. Well, great, perfect. But there's no real kind of overarching law that says this particular force has to operate. So too with the elementary particles. They kind of fit together nicely to create all this stuff that exists in the universe. But there's no real rule that says that these particular particles have to exist. No, they just do exist. It's like cracking open an IKEA box and you see all the parts and the instructions inside, and the idea is go ahead, build a universe out of that stuff. This is the stuff that is available to you. So as soon as we get to this idea of certain irreducible elementary things, we're kind of pressing up against the idea of, well, this is far as we can go towards understanding stuff. And as I say, we can understand a lot about how things work just by looking at how these particles and forces interact together, but we're also pressing against the kind of inexplicability of them even existing in the first place. So we'll take the break here and come back with the rest of it.